A very good morning, girls. So, to start with today's class, I just want to start it on a positive note. Your limitation, it's only your imagination. What is the meaning of it is what I can do now, what you fix in your mind. This is what I can do. If you limit yourself, that is only your imagination. So, in your mind, if you think, I can do all this, that means that becomes your limitation. So, it is not in terms of any external factors. Our limitation for our mind is given only by us. So, I want you to just remember that. To put this in other words, there is no limitation for ourselves. It is only what limits we fix. It can be in terms of your studies, it can be in terms of your dreams, anything. What limitations we have is only our imagination. So when you keep yourself positive, when you keep yourself like there are no limits for me, I can achieve this if I start doing it, then definitely everything is possible in life. So on a positive note, we are all very strong and we know that everything is possible when we keep our mind focused on whatever we do. So our limitations are not what somebody else gives us. It is only what we give to our imagination. So on this note, a very good morning and let us get into our session today. The winners of yesterday's quiz. First answer was by Preeti N, second was by Preeti S, and all these girls gave the correct answers at the same time. So it's Arshia, Steffi Margaret, Swati, and Ramya P. Congratulations to all the girls for taking up the questions and answering them correctly. So congrats to both the Preetis, Preeti N and Preeti S, Arshia, Steffi Margaret, Swati, and Ramya. So when we go to today's class, yesterday we were seeing few properties of how is the charge behaving on a conductor. So we did with 5 points. Continuation of that, the 6th point is these surface charge distribution may be different at different points. I'll show you a diagram, you will be able to easily follow it up. See, we have a conductor here. The shape of the conductor is not uniform. It is, you have a bulge surface here and the other surface is the sharp end. See, the area of this surface near the curve is more, whereas area of the surface near this edge is less. So this is an example for irregular surface. According to the properties of charges, near any sharp edges, more number of charges will accumulate. You have the habit of eating an ice cream, cone ice cream you've seen, right? So the tip of the cone, if you pour anything inside the cone, automatically everything will drain up to the bottom where we have the sharp end. As that end fills only, you will see the upper layer filling up. The same way, when we have any sharp surface, just like a cone, near the tip or near the sharp edges, more electrons will be present than compared to the broader edges. So you can see the surface here. Here they are broadly distributed, little far. But here if you see, inside the small region itself, there are 3 charges present. You take the same amount of region towards the other end, you will have only 1 charge present here. So surface charge distribution may be different at different points. It is not uniform. Near the sharp edges, more charges will accumulate than compared to the regular surface. So that is one point to add up. So today's class, see the sigma minimum is surface charge density is minimum here. Here sigma density means surface charge density is more. We are going to study about what is the meaning for electrical potential or what is the meaning for your capacitance. See, the formula for your surface charge density sigma will be Q divided by S. Q is the charge and S is the surface area. Every conductor is an equipotential volume. If I consider the volume, it should be in 3-dimensional. If I consider the surface, it will be only in 2-dimensional. So every conductor will have an equipotential volume in 3-dimension rather than equipotential surface in 2-dimension. So keep this in your mind. Volume is a 3-dimensional quantity. surface is the two-dimensional quantity, and a conductor will always have an equipotential volume compared to an equipotential surface. Now we'll go into the definition for electrical capacitance. Very important 2-mark question. The measure of the ability of a conductor to store charges. That's all is the definition. It is the measure of the ability of a conductor to store charges. How much of charges it can store. That ability is called as capacitance. The older name for capacitance was capacity. Now you take a small beaker or a bottle, any thing which you're going to fill inside. No, we will ask, what is the capacity of this bottle? Say it's a half-liter bottle or it is a 1-liter bottle. What is the meaning for it? It can hold half-liter of any liquid or half-liter of water. For example, you go buy Bisleri bottles. One small bottle is half-liter bottle. What is the meaning for it? It can hold half-liter of water. So its capacity is half-liter. So what is capacity? How much can be stored inside it? The same way, the measure of the ability of a conductor to store charges, we call them as capacitance. I want you to quickly learn up in your mind. The measure of the ability of a conductor to store charges, we call them as capacitance. I want Dhanlakshmi to answer. What is capacitance? Sneha Purushottam has already lifted her hand. Yes, Sneha. What is capacitance?
The measure of the ability of the conductor to store charges is known as capacitance or capacity.
Very good. Savina, you raise your hand.
The measure,
Yes, ma'am. What is capacitance?
the measure of the ability of a conductor of stored charges is known as capacitance or capacity.
Very good. So others also have raised hands. We have Vishalakshi, Kavishri, Usha, Pooja, Swati, Nancy. So I will go on to the next definition and ask you questions, okay? So this measure of ability of a conductor to store charges, we call it as capacitance. Now what is the formula? Q will be proportional to V. Q is your charges and this will be proportional to V, which is your potential difference. To remove the proportionality sign and put an equal sign, we should have one constant. That constant is denoted by the symbol C. So charges is proportional to the potential, or charge will be equal to capacitance multiplied by your potential. So from this I can write C equals Q divided by V. This is our formula for capacitance of a conductor. Capacitance, very simple definition. It is the ability of a conductor to store your charges. What is our formula? C equals Q divided by V. If V equals 1 volt, if the potential is equal to 1 volt, in this formula, V value will become 1. So what will happen to the expression? C should be equal to Q, meaning capacitance should be equal to the number of charges when the potential will be equal to 1 volt. That is one condition what we have. Capacitance of a conductor is also defined as the charge required to raise the potential through 1 unit. So capacitance of a conductor is also the charge required to raise the potential through 1 unit. This is the second definition in terms of your formula. Keep it clear. How much is the charge required to increase or raise the potential by 1 unit is also called as your capacitance of your capacitor or a conductor. SI unit for capacitance is farad. Farad means it's the name of the scientist who found it out. So F should be small letter, the symbol should be capital F. So for capacitance, it is farad. Farad is a very heavy, bulkier quantity. So what we do is we take it in simpler terms. I will tell you as we are going. For example, microfarad or millifarad or picofarad. That is how we take divisions. But generally, The SI unit of capacitance is farad. You can see the symbol. Two parallel equal lines will be there. Majority of our children make small mistakes here. See, when we draw a cell, one line should be bigger, positive line. One line should be smaller, that is a negative line. But if you draw a capacitor, both the lines should be equal and both the lines should be parallel. This is the symbol for your capacitor or for capacitance. Capacitance will be said to be 1 farad when 1 coulomb of charge raises the potential of the conductor by 1 volt. You see this definition here. C equals Q divided by V. So the capacitance is said to be 1 farad when 1 coulomb of charge, which is in the numerator, should raise the potential of the conductor by 1 volt, that is in the denominator. So seeing this derivation, you can write the definition for what is your 1 farad. 1 farad is when 1 coulomb of charge raises the potential of the conductor by 1 volt. Since 1 coulomb is the big amount of charge, the capacitance will usually be in the range of millifarad. Please make a note in your book. Milli is 10 to the power of minus 3. Millifarad is 10 to the power of minus 3. Microfarad 10 to the power of minus 6. Micro is 10 to the power of minus 6. Or it can be nanofarad. Nano is 10 to the power of minus 9. So nanofarad means 10 to the power of minus 9. Picofarad is the last one. It is 10 to the power of minus 12. I'm repeating. Milli is 10 to the power of minus 3. Micro is 10 to the power of minus 6. Nanofarad 10 to the power of minus 9. And picofarad is 10 to the power of minus 12. I want Usha to answer. How much is nanofarad?
10 to the power of minus 9.
Very good, Usha. Anita, what is microfarad? Anita? Hussefa? Microfarad?
Ma'am,
What
10
is
to the power of minus 6.
micro? 10 to the power of?
Minus 6.
Very good. Kavishri, millifarad?
Ma'am, 10 to the power of minus 3.
Very good. Swati K, picofarad?
10 to the power of minus 12.
Very good. Who can tell me all the 4 now? Aisha will try.
Yes, ma'am.
How much is milli?
Millifarad is 10 to the power of minus 3.
Very good.
Microfarad 10 to the power of minus 6.
Good.
Nanofarad 10 to the power of minus 9.
Very good.
Picofarad 10 to the power of minus 12.
Very good. Very good, Aisha. I will tell the number now. You'll tell me what is the power, okay? Name.
Yes.
Kirtana.
Yes, ma'am.
10 to the power of minus 3 is called what?
Millifarad, ma'am.
Okay. 10 to the power of minus 12?
Picofarad, ma'am.
Very good. 10 to the power of minus 6?
Microfarad, ma'am.
Very good. 10 to the power
Microfarad,
of
ma'am.
minus 9?
Nanofarad, ma'am.
Very good. So I think you are clear with this. So this definition for capacitance, SI unit, and the range symbol, 2 parallel lines should be drawn. We'll move on to the next one. Capacitance of an isolated spherical conductor. So what is this capacitance of an isolated spherical conductor is? You can see a circle here. So we'll imagine that is our spherical conductor. I will imagine the center of the spherical conductor to be O. Let a charge be placed at a distance r from the center, and the charge will be denoted with the symbol plus q. I'll write the definition now. Let a charge be given to the sphere which is assumed to be concentrated at the center. potential at any point on the surface. Now, at any point, the potential will be denoted by the formula V equals, generally we write it as 1 divided by 4 pi epsilon naught Q divided by R. That is the general formula from your Coulomb's law. I've combined it and I'm writing it like this. V is equal to Q divided by 4 pi epsilon naught into R. The next step will be, our definition formula is C equals Q divided by V. See if you're comfortable with both. For potential, my formula is V is equal to 1 divided by 4 pi epsilon naught Q divided by R. Multiplying, you will get Q divided by 4 pi epsilon naught into R. That is the first definition. Second one, from definition of your capacitance of your capacitor, C is equal to Q divided by V. Okay. Rearranging this, you can write V equals Q divided by C. That is, C will come down to the denominator and V will go up. V equals Q divided by C, the same expression. Now here also I have V, here also you have V. So we can equate our right hand side. Q divided by C will be equal to Q divided by 4 pi epsilon naught into R. Cancel out Q and Q. What is remaining? 1 divided by C will be equal to 1 divided by 4 pi epsilon naught into R. Again, I can cancel out 1 and 1 which is in the numerator. So we will get C equals 4 pi epsilon naught into R. This is the formula for capacitance of an isolated spherical conductor. I'm repeating it. We are considering a charge Q to be given to the sphere, which is assumed to be concentrated at the center. Potential at any point on the surface is assumed to be concentrated at the center. Potential at any point on the surface is V equals Q divided by 4 pi epsilon naught into R, or capacitance C will be equal to Q divided by V. This formula can be rearranged. V is equal to Q divided by C. Equate both the sides. Q by C will be equal to Q divided by 4 pi epsilon naught into R. Cancel Q on both the sides. 1 by C will be equal to 1 by 4 pi epsilon naught into R. Or you will get C is equal to 4 pi epsilon naught into R. Pooja, you want something? You have raised your hand. Pooja? Yes.
No, ma'am. No, ma'am.
Okay. So first point, what you have to learn here is capacitance of a spherical conductor is directly proportional to its radius. C is capacitance, R will be your radius. Second point, the above equation is true for spheres, conducting spheres, anything which is round in shape, or for a hollow or solid sphere. Hollow means empty, or a solid sphere also can be taken. For all conducting spheres, whether it is hollow or solid, this equation holds good. If the sphere is in the medium, this is in air or vacuum, epsilon naught. If it is in the medium, then C will be equal to 4 pi epsilon naught epsilon R. This is the relative permittivity of the medium multiplied by R. That is our formula. If it is in vacuum, only epsilon naught. If it is in the medium, you have to just add epsilon R. Capacitance of the earth value is 711. This is microfarad, or 711 into 10 to the power of minus 6 farad. Keep a note. Capacitance of the earth is 711 microfarad. Now, having seen this, 3 mark or 1 mark questions of chapter 1 and 2 which we are discussing, I will explain it to you. I will share it on the group for you. Go through. You have any doubts, we will explain it later. What we have left out is what are equipotential surfaces. So any surface where the potential is same at all points on the surface, that we call it as an equipotential surface.